Hello everyone. Dual nature of radiation and matter part 3. Wave nature of matter. In this video I will be discussing about the wave nature of matter. In this video the first topic that I will be covering is the de Broglie's hypothesis. In 1924 the French physicist Louis Victor de Broglie gave the hypothesis that moving particles of matter should display wave-like properties under suitable conditions. That is, he reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. According to de Broglie, the wavelength associated with a moving particle having momentum p is related as lambda, which is the wavelength, is equal to h by p, where h is the Planck's constant. This is known as de Broglie relation and the wavelength is called the de Broglie wavelength. Now, in the case of a photon, the momentum is given by the equation P is equal to h nu by c, where h is the Planck's constant, nu is the frequency of the photon and c is the velocity of light. We substitute this, that is h by p, we get c by nu, which is equal to lambda, the wavelength. Hence, it satisfies the de Broglie's equation. Now, the de Broglie wavelength is smaller for heavier particle or more energetic particle. This is why its value is very small in the case of macroscopic objects that we see in our everyday life. And the wave character of subatomic particles, which are very small, is measurable and is significant. For an electron of mass m having a charge E, which is accelerated from rest to potential V, the kinetic energy K of electron equals the work done on it by the electric field. That is, K is equal to QV. In this case, Q, which is the charge, is equal to E. Therefore, K is equal to E into V. Now, we know that the kinetic energy is given by K is equal to half mv square, which is equal to p square by 2m, where p is the momentum, or p is equal to root of 2m into K. That is equal to root of 2m eV. Now, if we substitute the value of p in the de Broglie equation, that is lambda is equal to h by p, we get it as this is equal to h by root of 2m eV. Now, if we substitute the values for the Planck's constant, the charge of an electron and the mass of an electron, we will get the value as 1.227 by root of V Newton meter, where V is the potential. Now we can see about the Heisenberg's uncertainty principle. According to the principle, it is not possible to measure both the position and momentum of an electron or any other particle at the same time exactly. There is always some uncertainty, delta x, in the specification of position and some uncertainty, delta p, in the specification of momentum. And its product is almost equivalent to a constant value which is equivalent to h by 2 pi, where h is the Planck's constant. Now, if we use de Broglie's principle, if an electron has a definite momentum p, then by de Broglie relation, it has a definite wavelength lambda. And a wave of definite, that is single wavelength, extends all over space. So if we use the Born's probability interpretation, it means that the electron is not localized and is in any finite region of space. That is, its position uncertainty is infinite, which is consistent with the uncertainty principle. It can be shown as in this figure. Now, in general, the matter wave associated with the electron is not extended all over the space. It is a wave packet which extends over some finite region of space. In that case, delta x is not infinite, but has some finite value depending on the extension of the wave packet. It is built up of wavelength spread across some central wavelength. This is as shown in this figure. Now we can see the Davisson and Germer experiment. This experiment proved the de Broglie hypothesis. Now we can see the setup of the Davisson and Germer experiment. It consists of a filament F made of tungsten which is coated with barium oxide. It is given a low voltage. Then a high voltage is used to accelerate the electrons emitted from the tungsten filament. A is used to collimate the electron beam which is produced by the heated tungsten filament. The collimated electron beam is accelerated by the high potential and it falls on a nickel target. And after scattering from the nickel target, the electron beam falls on a detector. And the detector consists of a movable collector which is connected to a galvanometer. And the galvanometer shows the current depending on the intensity of the electron beam falling on the detector. Now the experiment was done by varying the values of the high voltage, which is the potential used to accelerate the electrons, and theta is the angle between the incident electron beam and the scattered electron beam. Now the experiment was performed by varying the accelerating voltage from 44 volt to 68 volt. It was noticed that a strong peak appeared in the intensity of the scattered electron for accelerating voltage of 54 volt at a scattering angle theta is equal to 50. Now the appearance of the peak in a particular direction is due to the constructive interference of electrons scattered from different layers of the regularly spaced atoms of the crystal. From the electron diffraction measurements, the wavelength of matter waves was found to be 0.165 Newton meter, which was found to be equivalent to that found by using the de Broglie's principle. So this is the end of this video. In this video, I had discussed about the wave nature of matter. If you got any doubt, please do comment in the section below. Thank you.